I can get quieter and louder. Yeah, you're talking. I hope. Otherwise we'll have a different problem.
Hey, Katie. Good to see you again. Nice to see you. You're moderating?
I am.
Nice. Exciting.
Well, you see the timer, so.
Yeah. That should be good. Yeah. Yeah.
Closer.
Yeah. I think I'll be just beyond the 12-minute mark, but it should be good. Yes. Yeah.
Hello. Okay, I think it's time to start the next session of the Spring Symposium. And our speaker is going to be Viraj Pandya, talking about the expandable galactic atmospheres and the physics of galaxy self-regulation.
Okay, thank you so much, Katie. So I'm Viraj Pandya. I'm a Hubble Fellow at Columbia, and I'm very excited to share some new models that we've been developing in which galactic atmospheres play a key role in regulating star formation. So I want to start by highlighting, as we've heard all week, that there are a number of amazing cosmological zoom-in simulations that can make detailed predictions for things like galactic structure and the emergence of the Kennigan-Schmidt relation, the launching of multi-phase outflows, and the properties of the multi-phase circumgalactic medium. So these simulations are great for predicting things like this, but they're also very complicated to understand. They're also very expensive, and so many of us in this room are interested in developing simplified models that begin to explain the physics of what's actually going on in these kinds of complicated numerical experiments, and that really enable fast and robust Bayesian inference using a lot of the exciting observations that many of you are obtaining. And so simplified models of what exactly? So models that address this question of how do galaxies co-evolve with their host atmospheres. And so why is this so important? Well, you heard from Chris Carr just before the coffee break, and you'll hear again from Greg Bryant in the next talk, that the CGM may constrain feedback processes. The CGM may regulate star formation by modulating inflows of gas, the fuel for new star formation, and the CGM may hold information needed to break parameter degeneracies in our models of galaxy formation. And so with all these things in mind, we've been developing a new framework that we're calling Sapphire. It doesn't stand for anything yet. It's really just a model where you treat galaxies like the complex dynamical systems that they are, but without the full degree of complexity that you have in like full-on hydro simulations. And so what do I mean by that? Well, you start by writing down a set of state variables. These are things that you want to keep track of for your galaxy and its cosmic ecosystem as a function of time. So things like, for example, the mass in the atmosphere and the ISM in the long-lived stars, the metal masses in these three components. And then once you have this, you write down the corresponding system of coupled nonlinear ordinary differential equations that tell you how these state variables co-evolve as a function of time. And so each of these terms on the right-hand side represents a different physical process and has to be parameterized in a physically meaningful way. And semi-analytic models have been doing this for decades. But the new thing that we've done is we've added in new ODEs that let you predict the thermodynamic evolution of the CGM and explicitly let you connect the CGM, couple the CGM to galaxy formation. And so before the coffee break, Chris Carr already introduced our new ODE for the thermal energy evolution of the CGM, but there's one other very important component of the CGM energy budget, and that is turbulence. And so in the full model here, we also have an ODE that tells you, for example, how cosmic accretion and feedback drive turbulence, and then how that turbulence dissipates into thermal energy over some time scale. For those of you that are visual learners, you can translate this maybe complicated, scary-looking system of equations into graphical form. And this illustrates that all of those m dots and e dots in the previous slide really just reflect flows of mass, metals, and energy into and out of galaxies and their surrounding atmospheres. And you can really summarize this framework in just a few key lines. And so this is really, we've been developing a model where explicitly for the first time, we can tell you how to couple feedback energy, not just the mass ejected via feedback, but also the energy of feedback to the CGM. And so we think, in this framework, we can allow for the possibility that galaxies eject these high specific energy outflows. Those outflows can then heat and stir turbulence in the CGM. They can prevent cooling and accretion of that atmospheric gas into the galaxy, and therefore regulate star formation. And so in frameworks like this, you always have a number of free parameters that encode your ignorance about various physical processes. And so we have about 10 parameters that we think is the minimal set of parameters you need to encode your ignorance about, for example, star formation, about feedback, about chemical enrichment, and about how turbulence is driven and dissipates over some time scale. And the cool thing is that just by choosing reasonable values for these parameters, we've shown that you can actually get very close to explaining and reproducing the evolution of individual simulated galaxies in cosmological simulations. So for example, we can reproduce the mass assembly histories of the CGM, of the ISM, and of the long-lived stellar population of individual halos in the Fire 2 simulations, for example. We can also reproduce scaling relations between halo baryon fractions versus halo mass and redshift. And we can reproduce mass metallicity relations. But the really new thing that we can do with this kind of framework is because we're tracking energy flows through the CGM, we predict that the CGM has to undergo this phase transition. In the sense that, for example, for a Milky Way halo, at early times, the CGM may be very cool because the cooling times are very short, but also cosmic accretion and turbulent feedback may be driving turbulence. And so the CGM at early times may be very cool, but it's also very turbulent. And so there's large-scale pressure support that can hold up this cool gas, prevent it from falling into the galaxy and forming too many stars at early times. And then at some point, there's a rather abrupt transition that we call thermalization, where the CGM approaches this warm, hot temperature, like we're familiar with for the Milky Way at low redshift, for example. So all these things are very exciting, but as is the case with models of this type, you're always sensitive with these predictions in terms of what you choose for the values of your free parameters. And it's really, the sensitivities of these kinds of models, the degeneracies in these kinds of models between these parameters is really largely uncharted territory. And so we've also written Sapphire in this lightweight machine learning package called JAX, which really accelerates our modeling that we can do for galaxies and their CGM. But the really unprecedented thing that we get and that defines Sapphire is we get gradients of the model with respect to variations in all of its free parameters. And so for the first time in the 50-year history that people have been creating models like this, we have the full Jacobian matrix, the sensitivity matrix, as a function of time for lots and lots of halos. And so here I'm showing you just two columns of a much longer Jacobian matrix. Don't worry about the numbers, just focus on the colors here. The first column is the sensitivity of these state variables at redshift 0 to perturbations in the mass loading parameter. You can see that this column is grayed out. The model, as Chris Carr said earlier, is not sensitive to changes in mass loading. But it's really changes in the energy loading, the second column, that the model is very sensitive to. And so in this paradigm, it's really the energy loading, the energy content of feedback that is regulating star formation, the ISM mass, and even the chemical enrichment history. And so these gradients and acceleration for the modeling really unlocks brand new techniques for Bayesian inference. And one of the things that I want to highlight, I've been working with Lucas McKinnon, a grad student at Imperial College in London. We've been using the hot new thing in Bayesian inference, implicit likelihood inference, where you generate a bunch of realizations of your model with different parameters. So we varied our supernova wind energy and mass loading parameters, generated lots of realizations, and then we are asking, can we train a neural network to learn the mapping between these mass and energy loading parameters and the outputs of the model? So if the only thing we give the neural network is the stellar mass and halo mass of galaxies in every realization, it cannot learn the mapping between, it cannot learn the mass loading parameters because, as I showed you in the previous slide, the model is insensitive to variations in mass loading. But it can learn the energy loading parameters because the stellar mass halo mass relation is sensitive to the energy loading. So the next obvious question is, what if you fed the neural network additional information about the galaxies and the CGM and all these realizations, like the gas fractions, the temperature of the CGM, metallicity information. So when you do this, the neural network can beautifully recover and learn the parameters of the model governing feedback. And so this is really just telling us what we've known for a while, that the gas, the CGM, we think contains the information needed to constrain the parameters of these kinds of models. So I can say a lot more about this, but I want to advertise an amazing bridge student at CUNY, Austin Gabriel Pillai, who has also been working to implement satellite galaxy evolution in this new framework. And so this is preliminary, but we're finding that we are able to reproduce, for example, the satellite mass function of Milky Way satellites, but we need to add reionization to further suppress star formation in Milky Way ultrafaints, and we need to add ram pressure stripping, which now our CGM model provides the ambient conditions for, to strip the gas in pretty much all Milky Way satellites except for the most massive ones like the LMC and SMC. And then we can also reproduce the stellar mass metallicity relation of Milky Way satellites, but we need to also pre-enrich the Milky Way ultrafaints with metals from the Milky Way's own winds at early times, for example. So there's a lot more I can say about that, but I want to end by advertising one other thing that we are doing. So we've been working with Mark Voigt on another very cool extension that we're calling XCGM, or Expandable Galactic Atmospheres. And the idea here is to explicitly track also the gravitational potential energy of the CGM, and then assume that that is balanced by the sum of thermal and non-thermal pressures in the CGM. And so this lets you predict then the structural evolution of the CGM. And the key idea here is, as you increase the specific energy of the CGM, as you overpressurize the CGM, for example, due to feedback, it literally has to expand to a larger radius, such that within that larger radius, there's going to be a smaller enclosed pressure, such that you're still maintaining force balance against gravity. And this is really, really exciting, because we think it unlocks a new observable that you can predict with these kinds of intuition building models, and that is the extent of the CGM. The extent of the CGM, and we can predict how that CGM radius depends on what you assume for feedback or the nature of turbulence in the atmosphere. And in this framework, I'll just say, the extent of the CGM sets the density profile, which then determines the cooling rate of gas into the galaxy. And so in this model, you're directly regulating star formation via this expansion and contraction of the CGM. So stay tuned. We're going to be releasing an amazing online textbook that Mark has been writing, and I've been writing Python code so that all of you can gain intuition for how to use these kinds of models. And we're also starting to think about ways to actually predict observables with this kind of framework to do Bayesian inference. So I'll stop there, and I'll also advertise, stay tuned for the eventual open source release of this JAX-based Sapphire code, where we hope we can infer the parameters not just of galaxy formation, but also of how halos and the CGM evolve. So thank you very much. I'll take questions if we have time.
I see 2 questions over there.
You briefly very briefly mentioned you need to pre-enrich satellite galaxies. Why is that? Can you?
So if you assume that the satellites are only enriched by their own star formation, you get, I mean, there's just not, there's not enough metals.
Can't you change the star formation history of these, or star formation time scale of these galaxies? What's the other constraint that you have to set such inefficient chemical enrichment in?
Yeah, there's some wiggle room in the star formation histories, but also I'm talking about the lowest mass galaxies, and these are heavily affected by reionization, which means that essentially all of them have to form very early anyway. And so they have to get their metals from somewhere else, probably. And the Milky Way, the ambient medium is one way to get those metals. But you're right, there is some wiggle room in maybe extended star formation histories, and Dan Wise has some interesting constraints on that.
Hi, thanks, very interesting. I'm wondering about this Bayesian inference model, and I'm wondering how often it's able to find unique solutions, and I'm also curious about if there are situations in which you have a degeneracy between two solutions that match well, as opposed to an insensitivity like you see with the mass loading factor.
Yeah, that's a great question. So we're still mapping that out. With the gradients, we can explore parameter space very quickly with new techniques, and so stay tuned for results on degeneracies, which is still a work in progress. On that note, I'll just say metal loading is another important thing in addition to energy loading, that we think there'll be degeneracy there for a lot of the stuff with chemical enrichment.
One more question.
Very nice talk, Viraj. I wasn't sure if I missed it or not, but these parameters that describe in the CGM, are they like phase dependent?
Are they phase dependent?
Yeah, how do you, like for example, the temperature, is that for a specific phase or?
Yeah, great question. So in this first baseline model, it's still a single phase model, but we've been thinking about extensions to introduce additional phases. And so right now, like these CGM parameters, they describe a one phase, one zone CGM model.
Okay.
Let's thank our speaker again. Our next speaker is Greg Bryan, talking about the Arkenstone, simulating CGM-based star formation regulation with high specific energy outflows.
Thank you very much. So this is the third talk in the series. You heard before the break from Chris Carr, and then you've just heard from Viraj Pandya. So I want to continue on this theme of high specific energy, of talking about the importance of energy in regulating star formation. And so I want to motivate part of this just by putting things a little bit in context by reminding you about where star formation regulation occurs. Of course, it happens on the smallest scales, on the molecular cloud scale, where ionizing radiation and jets and eventually supernova perhaps regulate star formation in molecular clouds. It also happens on the ISM scale. Supernova actually inject momentum into the ISM and drive turbulence. And as Chang-Gu Kim talked about a few days ago, this helps regulate star formation on that scale. But it's this third scale, the circumgalactic medium scale, that I want to focus on today. And as we've just heard, there's a growing sense that this is an interesting mechanism. These energy flows are an interesting mechanism for regulating star formation on this scales. So you just heard two great talks, which I think give you the answer which is that energy flows do indeed, or can indeed, regulate star formation on the largest scales. And I want to turn to maybe the question, which is, can we do this using numerical simulations? And as Freaky demonstrated earlier, there's a lot of uncertainties in how this energy and outflows in mass are actually implemented in simulations. So I want to talk a little bit about simulation. So here's M82. You've seen this before. I want to talk about how a simulation of this might work. So we turn it on its side, draw a little box around, and then do a simulation of just the star-forming region within this region. So here's the plane of the disk. We put in a star formation burst, so this is not intended to exactly match M82, but it should roughly model this kind of outflows that we expect in these simulations. And what you see is that, and this is characteristic of all these simulations, is you see this hot, very diffuse 10 million degree outflows, and then lots of little clouds entrained in these outflows. And so we can measure the mass and energy outflows rates in these simulations. This has been done for other simulations. I don't want to belabor this point, except that there are these two modes that we see. The cold mode, bringing mass out of the typically cold mass out of the galaxy, and then this hot mode, which brings energy out. As you've just heard, if we focus on the energy part in particular, this is a great mechanism for building galaxies which match observed scaling relations. How can we go about simulating this? In cosmological scale simulations, where we don't have the kind of resolution that I just showed you in that simulation that focused on a star-forming burst on a region. And of course, there's two challenges that we face. One is a familiar one, which is that cold clouds, those cold clumps you saw in the outflows, are small. They're really hard to resolve in numerical simulations. You saw some beautiful simulations earlier. As you add additional resolution, you see a finer and finer network of these things. But I want to emphasize that this isn't the only problem that we face. The other problem is that these hot diffuse winds are big. And that sounds a little odd, but let me get to that in a second. So let me take the first problem first. So here's a couple of these clouds. If we focus in, again, adding even more resolution and look at an idealized simulation of a cloud with a wind hitting it, then what we see is these clouds are generically destroyed. Their mixing time is shorter than the time it takes to accelerate them. There's the equations, but the point is that the interface drives turbulence, which mixes the clouds away faster than they can absorb the momentum of the outflowing gas. So actually, this is a problem that was pointed out almost a decade ago, that if this is the only thing operating, then there's no way to drive these cold clouds out of galaxies. Fortunately, I'll say, so that was, we can use this insight to generate a formula for the rate at which the clouds are destroyed. And this will become important in a second. As I was saying, fortunately, that's not the only process. If cooling is occurring, then this very same simulation, if we change the parameters such that the turbulent radiative mixing layers which form at the interface of this cloud and the hot wind are cooling efficiently, then these clouds don't just survive, they actually grow in mass. And so simulations like this can show you that can be used to compute a simple formula for the rate at which this cloud grows, which depends just on the mass of the cloud and this ratio of the mixing time to the cooling time at the interface region. This allows us, these two insights the rate at which the clouds are destroyed and the rate at which the clouds grow can be combined to have a simple formula which describes how these a cloud embedded in this hot outflow would evolve. And it depends just basically on the cloud mass and on this mixing time to cooling time ratio, such that basically large mass clouds grow more rapidly, whereas small clouds are destroyed quickly. So that's one part of it. So we have now a better picture for how these cold clouds operate. But let's talk about the second problem. These hot diffuse clouds, so cosmological simulations, and this is an insight actually I only realized a few years ago, cosmological simulations, because they used fixed mass resolution, actually really struggle to represent hot diffuse regions. So the typical resolution in a large-scale cosmological simulation, like Illustris or Eagle, might have a resolution something like that. And this then sets, along with the density, the size of the cloud through this simple relation. And so if we take the low-density regions, which we expect in these hot outflows, then which are very, very low, then the resulting cloud radius is very large. So this cloud radius might be as big as the size of in fact, you can see in that individual cloud sizes as big as the radius itself. So to solve these two problems, this cold cloud problem and this hot outflow problem, we've developed this two-phase cosmological subgrid model, which we call Arkenstone. And the basic idea is that we explicitly try to model this hot outflow part, which is responsible for the preventive feedback that you just heard in the last two talks, as well as this cold phase, which is responsible for the ejective feedback. And this is Matthew Smith, who is responsible for implementing, coding this up in a repo. And there's a paper already on describing the hot part of this, and there's another paper coming in the next month or so describing the cold part. And I'll just quickly describe what is involved here. So to solve the hot part problem, the solution in some ways is very simple. We just add additional resolution. You know, these cosmological simulations like a repo don't have to have fixed mass resolution, and we exploit that fact by having the wind add an additional tracer fluid, which decays after a certain amount of time, but that tells it to add additional resolution. So this shows the resolution in one of these simulations. This is pre-Arkenstone, and then the right is Arkenstone with this resolution on, and you can see that the outflows produce very high resolution regions right where you want them, where you need to be able to resolve the thermodynamic transition from hot gas moving slowly to cooler gas moving quickly. So there's a sonic point, and that happens only a few kiloparsecs above the disk. So you need that resolution there. So that's the hot part. Oh, and just to show you that this actually has an effect, here is on the right-hand side. Here is a high mass-loaded simulation. So this is what might be done with cosmological simulation, which adds a lot of mass outflows. And you can see it's operating in this juggling mode. It actually correctly reproduces the stellar mass-halo mass relation, but it does it by just throwing mass up into the halo and letting it come back in. So on the other hand, once we implement Arkenstone and we can resolve these very high specific energy hot outflows, then we see a very different kind of process. Much more, driving much more energy out into heating the circumgalactic medium and doing the kind of regulation that you heard about before. So the hot part, so we separate the phases, and this allows this regulation that you heard about in the last two talks to correctly match the observed scaling relations. So the second part, this cold cloud part, is is also the second part of Arkenstone, and this is the second paper, which is coming out soon. And the idea here is to try and use that insight that I talked about before, right? That these cold clouds immersed in a hot outflow have a simple set of scaling relations which tell us how mass, momentum, and energy flow between them. So we've calibrated those on very high resolution simulations. And then what we can do is we can just add particles which represent a population of clouds. So this is again an ARIPA simulation focusing on a 10 to the 11 solar mass, halo mass galaxy. And what you can see here is this population of cold cloud particles. And each one of those is actually not just a cold cloud, but it actually represents a population of cold clouds, which so each one of these is actually a whole distribution of cold clouds, and with different masses, and we can use this simple formula that we derived before to compute how mass, momentum, and energy are transferred between the hot phase and the cold phase. So to be clear, these are not ballistic particles which are just shooting out, but are actually interacting with the hot phase. So perfect timing. Here's my summary. I want to emphasize a couple of things. One of which is that everything I've described so far is a pure methodological innovation. This is in some way an instrumental talk in the sense that we're developing new computational infrastructure. I show on the right a very hot off the press from just a week ago or so application to a cosmological zoom simulation. And the other thing I want to point out is that what I'm really excited about is using this technology to make synthetic observations. Thank you very much.
I'm already seeing questions. We'll start over there, and then I will come over there.
Do you expect that the two-phase treatment matters more at lower resolution? So like increasing resolution means that like maybe you wouldn't necessarily need the two-phase treatment, or that it impacts the evolution a little bit less?
Absolutely. No, I think that's a really good point. And because of course, as we go to higher and higher resolution, we resolve the cold clouds, the hot phase. So if we expect this to be most important in the large-scale cosmological simulations, absolutely.
I saw a question way back here. I am going to go all the way to the back.
Thank you for the good talk. I have a question. If I understand correctly, when you're tracing the cold phase, you actually spawn some new extra cold particles, right? So. Yes. When this particles is in wind, it's okay because they are decoupled with hydra. But after they just recoupled with the hydra, will this make your hydra part slow down? How will this make you? Make your whole cosmology simulation slow down much?
Right. So just a quick clarification. I want to emphasize that these are not decoupled. They are coupled to the hot phase. They exchange mass, momentum, and energy. It's just a different way of representing that. But you raise an important point. And what we actually do is eventually, once the clouds are, for example, destroyed or mixed in, then we actually end up recoupling that back into the hydrodynamics. For exactly this reason, we don't want a bazillion of these UMPs, these unrefined massive or under-resolved massive particles flying around using a lot of computational time.
Okay, I'm going to take two more questions, and I'm going to prioritize early career folks. So I see a question over there.
Yeah, hello. Really nice. I'm really excited about the prospects of synthetic observations. Question I had was, it seems like, when you're creating winds that might have hot and cold phases, you're injecting these particles. And I'm wondering about, in a more cosmological context for accretion, if cold gas is coming into the halo from outside, do you have any coupling there where you introduce the particles as well, or is it purely for generating in the winds?
So that's a great point. In fact, right now, the spawning is only associated with star formation feedback events, and actually we're adding it now to black holes as well. But we've actually discussed this idea of spawning them during the accretion event. So being able to better resolve, for example, if cold inflows. And actually that was one of the reasons why we chose not a two-fluid method to do this, but this particle method so that we could have interpenetrating cold flows. Yeah.
Thanks.
Okay, last question.
So you mentioned about creating the synthetic observations, and I'm curious about how confident are you for the predictions of warmer phase, like the warm phase?
Yeah, so that's a great question. So I didn't have time to talk about that, but we've developed a model for what's happening at these turbulent radiative mixing layers, because that's where we expect to see, the cold phase is on the inside, but the sort of warmest skin layer phase is on the outside. And we hope to be able to use that model coupled with this infrastructure in order to make exactly those predictions. Yeah, for X-ray emission and absorption.
I know there are still a lot of questions, so I will suggest you take them online or during lunch. And let's thank our speaker again. All right. Our next speaker, who I will wait for me to, okay, waiting, great, is Lori Porter, Growing Pains, Quantifying Superbubbles and Their Feedback in Fire 2.
Wonderful, thank you very much. So I have the wonderful and impossible task of going after Greg Bryan, and I will also be heading up the Columbia train after Chris, Viraj, Greg, and now me. So my name is Lori Porter. I'm a first-year graduate student at Columbia University. This work was done with Matthew Orr and Blakesley Burkhart, along with members of the FIRE collaboration. And as a quick little I will be the next one to show you this slide for the umpteenth time, but this is more for clarification. We have been talking about very large scales of the CGM and how that is regulating galaxy formation and the corresponding properties. But this study is actually going to focus on a much, much smaller scale. Because we are going to be talking about superbubbles, the winds they launch, and the turbulence that they drive. So we heard yesterday from a couple of talks, and we've heard a little bit today about just the importance of superbubbles. We know that they form from clustered star formation, and we know from people like Drummond Fielding, you must have clustered star formation to help reproduce some of the observed galaxy scaling relations. They drive some of the largest winds, because stars in a cluster of similar ages, when they start going off in supernovae, their shock fronts will couple together to form one large shock front. So this is mostly made up of a volume-filling diffuse hot gas. As Greg mentioned, they have a multi-phase nature. That hot gas is sweeping up cold clouds, and then this forms an outer shell of cold gas in the superbubble. And this dates back all the way back to some of the original superbubble papers in 1977. So this is pretty well predicted, and it's exactly what we end up seeing in observations of superbubbles. So these are extremely important, but we know that they drive all of the things that we've been talking about at this conference, such as the mass metallicity relation. They're driving all of these winds. They drive what reaches the CGM. But these are extremely difficult to study. The multi-phase nature means that we need multiple different wavelengths to study them observationally, and then it can be incredibly difficult in simulations. How do we actually choose to measure the winds that they drive? So you've heard a lot about the FIRE simulations, and I'm going to tell you yet more about the FIRE simulations. So there is a suite of cosmological zoom-ins, which means we have an effective cosmological context. There are lots of mergers that are occurring during the snapshots I will be showing you. They have been well quantified. We have a multi-phase ISM that develops self-consistently. It does not need to be put in by hand. And we also have a mass resolution of about 7,000 solar masses. So this particular study uses about 5 SMC mass galaxies called the M11s. We have some mock Hubble images here. The metallicity relations, and these are fairly well constrained at redshift 0 from our 2022 paper. And we also use 6 Milky Way mass galaxies, the M12s. So we're going across a pretty diverse mass range. Even just among the dwarf galaxies, we have an incredibly diverse population. M11E up in the corner here, that is a merger that is happening right there. M11D is extremely starbursty. M11H appears to be forming a disk. We have like such a diverse range. We also look at several different redshifts. So we go all the way from cosmic noon to all the way now with redshift 13. Seems a little silly. But we're looking around cosmic noon and the local universe at redshift 0. So we choose about 10 snapshots from each redshift to help quantify the winds that we're going to be looking at. So all of these snapshots are about 25 million years apart. And it makes it kind of difficult to decide, like, how should we quantify these winds? This is not something that's implicitly put into the simulation. I can't just simply, it's not one of my outputs. Like, what is the mass loading? What is the mass flux? Most of the galaxies simulated here are at a much higher resolution, but because not all of them are, we want to keep our sample size large. So we're going to actually stick with some of the lowest resolution simulated galaxies in FIRE. So for outflows and loading factors, how exactly do we compute these? You were just presented with 3 excellent talks on what these are, so I'm not going to emphasize that again to you, but instead we take the output of these simulations and we generate spatial maps of all of the data. So this is an example of M12b at redshift 0, so we can see face on, we can see all of the spiral arms, we can see what this looks like edge on. One of these little pixels is about 750 parsecs on a side, and then when we calculate our quantities, we're taking like this thin slice through the galaxy. And this resolution is pretty optimal for this because it seems to be about the resolution of JWST at a redshift of 1, which means when we have all of these new studies that are coming out, of super bubbles from JWST, we're at a prime resolution to compare our simulation results. So again, how exactly do we define the winds that they drive? How do we calculate this? There are many different methods, and this turned from a summer project into a multi-year project as it goes, and many of you understand. Because no one seems to do this in the same way. You can use a spherical geometry. You could define like a certain plane or a certain height above the galaxy, but then you have to decide what height. Then you have to decide how should this change with your different galaxy types. So I would love to talk more if you have any questions about how we chose this. So we chose to end up defining a certain plane above and below the disk when you're looking from an edge-on perspective. I say disk, it is not necessarily only disks because again, we're looking at different galaxies, different redshifts. At a redshift of 0, we choose to use a height of about 2 galaxies gas scale heights above and below the center. For our higher redshift sample, we're going to use 5% of the virial radius. So like Viraj has done previous work on this in FIRE using much larger radii. This is, again, at a much smaller scale. So more of like ISM scale. We choose like the virial radius instead of like the scale height just at this redshift just because when these galaxies are extremely bursty and going through star formation, that then does directly affect the scale height. So we want something that's going to be a little bit more stable and a little bit more consistent throughout all of the starbursts. Another thing that you can look at is imposing a velocity cut on your outflows. Are you trying to determine only the most energetic outflows that are going to make it out to the CGM? Are you only looking at what is just going directly out of the galaxy? Do you care if you're including fountains or not? Just to ensure we're looking at what is directly, hopefully coming from these super bubbles, is we choose a velocity cut about 3 times the neutral gas velocity dispersion that is normal to the plane that we define our outflows. This is because a paper I will talk about later on superbubble breakout theory determines that this should be not only larger than the largest turbulent eddies in the galaxy, but about the breakout speed that we'll expect from superbubbles. So then now that we've defined how we're going to calculate our winds and our outflows, we can then calculate mass and energy flux and some of our loading factors. We also calculate like momentum flux, momentum loading, and then the metals. But because we have limited time, I'm not going to show you all of that. So if we immediately just go into the mass loading and what we end up finding for these fire galaxies. So we're going to have cold gas at around below 10 to the 5 Kelvin on top, hot gas on the bottom, and we are going to look at this as a function of star formation rate surface density. We're using the 40 million year average star formation rate. This is what we get for our galaxies, which is super interesting. So the orange is our Milky Way mass galaxies, and the blue are our dwarfs. We see there appears to be very little dependence on redshift. In the paper, which I encourage you to go look at, it will be on the archive next week, we do this by redshift instead of just bitting all of these together. But if we look at other simulations, like from Tigris, like Chang-Gu presented earlier in the week, if we look at some recent simulations of an isolated LMC mass or SMC mass galaxy from Ulrich Steinwandel, we see that our simulations kind of fall directly within the mass loadings of these other simulations. And if we use observations from Christy McQuinn, we also find that it appears that we go right within those observations. We see that the cold phase is barely carrying more mass. You can't really tell from this plot, but that's also another interesting result, is that we see very little difference between the phases at these parameters. If we move on to the energy loadings, you've heard all about how energy is really, really interesting. It's really important. And this is another really interesting result, is we see that our energy loadings in fire using this are so much higher than some of the simulations. I could tell you for hours, like many possible theories about why this might be, but because, again, limited time, let's talk after about why this may be. So what do we get when we look specifically at our super bubbles? So I have the energy flux here on the bottom, mass flux on the top, and then our spatial distributions over here. So again, cold, hot, gas, and our star formation rate. So let's go through 10 snapshots of the example galaxy that I mentioned earlier. I'll show you these again, so don't worry if you miss a couple things. So this is just all of the energy, all of the mass that is going out this galaxy during those snapshots. So this is the total distribution. Just in case you missed it, or maybe you weren't looking closely, didn't know what to identify, I've marked where we think superbubbles might be occurring in these snapshots. So each of these shaded gray regions, the darker one looks like to be a secondary superbubble. This first one, it's the snapshot before, snapshot during, snapshot after. What does that look like? So here we see that what we're seeing in fire appears to almost exactly match all of the superbubble expectations we've seen from previous literature. You see the shell of cold gas that gives you the bubble shape. We have the volume-filling hot gas component that breaks out, and you can see all of your star formation in your central stellar cluster. Stay tuned for more work on the fire collaboration about properties of these stellar clusters. So it looks like superbubbles may be what's driving some of the breathing modes of star formation that we see in these fire galaxies. And from our fluxes, we can see that they appear to be driving the largest galactic winds. And as a little teaser, because I am out of time, is I would also like to note the star formation rate in which you see. We've heard about how some of these energy fluxes and the mass fluxes may impact the star formation rate. Right after the superbubbles, when the fluxes drop, we then see the star formation drop as well. So I'm going to skip ahead to my conclusions that we have just from this. I would love to talk more, especially about theories about superbubble breakout and how they can then drive turbulence in the disk. But I would like to emphasize we need future work. We need to consider the physics of these simulations and impact of things like cosmic rays and cooling that may have on our results, because there's some results that say the implementation of cosmic rays can be a huge influence on whether you're actually driving outflows or whether they're just fountains. All right, thank you.
So, since we're running a little bit late in the session at a time that it would break into our lunch break, I'm only going to field 2 questions for the next couple of speakers because we also have a discussion section. So does anyone have a question? I'm also happy to do this. One more pause. I see a question back there.
So you mentioned cosmic rays. Do any of these large-scale sort of simulations take into effect cosmic rays? And if so, do you know what mechanisms? Is it just streaming?
So they do implement cosmic rays. I can't tell you the details about the mechanisms, but there has been recent work in the FIRE collaboration on affecting just the simplified transport of cosmic rays. For example, if we look at just Milky Way mass galaxies, if we completely eliminate cosmic rays, it looks like we're driving almost no true outflows. They're entirely fountains. And then the implementation of those simplified cosmic rays then leads to outflows being driven. So just some food for thought that we need to really constrain how we're implementing physics like that.
Any more questions? Okay, let's thank the speaker again. Our next speaker is Charlotte Christensen, speaking on the timescales and drivers of Milky Way satellite quenching.
All right. Hi, it's great to be here with you today. Yes, so we'll be talking about satellites. We've been hearing about the circumgalactic medium and how it can regulate star formation in the host galaxy. I'm going to turn this and talk about how the host galaxy circumgalactic medium can regulate star formation in satellites. And one thing I want to point out is that a lot of this work was done by a talented team of undergraduates, many of whom have now graduated, and one of whom, Anna Engelhart, you heard from yesterday. So this is simulation work. The suite of simulations I'm using is the DC Justice League. This was produced by the Chonga code. I've included some properties of the code up here. This is a set of 4 Milky Way mass galaxies and their satellites, and it was run with high resolution. All right, so if we want to figure out how these satellites quench, one of the first things we can do is look at how long it takes for them to quench. So this is showing quenching timescales versus stellar mass. So that y-axis is the time at which the satellite quenches minus the time at which it accreted onto the main halo, or crossed a virial radius. And you'll see that these satellites fill in different portions of this graph. So let me go back. We have our lowest mass satellites. These are satellites that quench long before infall. These are quenched through reionization. Our highest mass satellites, these are ones that in general have not quenched yet. So the blue diamonds with the arrows means these are lower limits. These are still star-forming satellites. And you can see I also have some observational points in here and also some simulation. But these are like your LMC or SMC. And then we have intermediate mass galaxies. And these are the galaxies that quench sometime after infall or around the time of infall. The vast majority of these galaxies quench. There are a few that are still star-forming, and most of them quench within a couple gigayears of infall. Okay, one thing I want to point out here is that there's a lot of spread during which these intermediate mass galaxies quench. So that's the next question. Why this range of quenching times? I'm going to skip ahead a little bit, but if you want to talk with me about satellites that have been destroyed, not the ones that we still see today, please do. I'd love to go over this work. This is done by Deb Pathak, who's currently a graduate student at OSU. All right, so our subsample are these intermediate mass galaxies. We're going to look at 19 of them and track their loss of gas. So we do this by tracking all gas particles that are ever part of the satellite after that satellite is first within 2 real radii of the main host. One thing I want to note is that our snapshots are spaced 300 million years apart. So that means that if there's stuff happening within that 300 million years, we're not going to track it. And what I want to do is I want to look at the ram pressure that these satellites experience. So this is a slide where I tell you how we calculate ram pressure. We're looking at the wind that the satellites are passing through by selecting the gas particles that are within a cylinder just ahead of the satellite. Right here, calculating the properties of that wind, and then comparing the ram pressure to the pressure that's due to a restoring force. Seen over here, that has to do with the surface density of the gas. And then I'll be talking about the ratio here, script P, way down at the bottom of the slide, the ram pressure divided by the restoring pressure. And you can see how this ram pressure develops over time for a particular satellite on the right-hand plot. And you can see that when we, there we go. These points where we have strong values of script P, you can also see a little tail of gas heading out behind it. And that's a signature of ram pressure. We can take this geometric signature of ram pressure and use it as a way to actually see how strongly ram pressure is acting on these simulations. So this is showing the angle at which the gas particles are leaving the satellite. Over here, we're seeing this for both gas particles exiting the satellite disk and exiting the satellite halo. And this is during the entire period of satellite infall. And then on the right-hand panels, we divided that up for satellites experiencing different values of script P. You can see our angle right here, 0 degrees, is that stream of gas heading out right behind, or that signature of ram pressure. To compare this, something like tidal stripping, we would see a double peak, as the stream was both ahead and behind. So we see this very strong evidence for the importance of ram pressure at removing gas. One thing we wondered about is, does feedback have any role in this? So we looked at, is there any difference between the gas particles that have been immediately heated by supernova feedback right before exiting the satellite? And if we look at the angle at which those leave the galaxies, over here, we can see not really. Whether or not these gas particles have been heated by supernova right ahead of time, they're still showing the strong signature of ram pressure. But it's still possible that supernova may be assisting, heating this gas particle up enough that it is more readily stripped by ram pressure. And we see some evidence for that over on the right-hand panel. So this is showing the fraction of the outflowing gas which has been heated by supernova. For low-mass galaxies, it's not very much. But once we get to our higher-mass satellites, we see that most of it, more than half in general, has been immediately previously heated by supernova. So this is an indication that supernova is still playing a role here. We also find that when we quantify this, supernova-heated gas is about 10% more likely to be permanently lost from the satellite. So some effect. Okay, so how does this gas loss progress during the satellite's accretion? What I'm showing here are cumulative histograms of gas loss, shown versus script P, or the ram pressure, the distance to the host, and time since 10% of the gas is lost. And you can see there's a wide variation in trajectories, but we can roughly divide this into two extremes. We have the light green. Those are galaxies that have very high radial velocities at infall. And these satellites, they lose their gas quickly, and they tend to lose it at low distances to the host and at high values of script P. However, that's not the only case. If you look at our blue and purple lines, these are galaxies that have low radial velocities at infall. They enter on more circular orbits. They lose their gas at large distances from the host and at low values of script P. Now, this value of script P is actually very low. We're seeing something like 1%, and that might be surprising. Probably a lot of this is due to the fact that we are looking at the ram pressure for the cylinder, and that cylinder is averaging out any dense clouds inside of it. So these satellites can be encountering a dense pocket of gas in the very outskirts of the host galaxy over here. That 300 million years spacing between snapshots might also be playing a role here. But big takeaway is that a lot of gas can be lost at these large radii. And if you want to see some alternative work on this, Simon's 2020 goes into a great deal of depth using the foggy simulations on how a highly resolved circumgalactic medium can affect satellite gas loss. You can also look at some firework that takes a different approach to looking at quenching from Samuel 2023. Okay, so we've been talking about gas loss, but gas loss is not the same thing as quenching a star formation. So let's try to finish out this circle. So here I'm showing the rate of gas loss divided by the gas mass in the galaxy. Each of these points is an individual snapshot or a satellite at a particular snapshot. And this is plotted versus distance to host. And we can see that as the satellite approaches the host, the fractional rate at which gas is lost increases. We also see that there's a change in the rate at which gas is accreted onto the satellite. So we see lower fractional rates of accretion at small distances. In other words, this is strangulation here. We see both effects are playing a role. Now we can look at the difference between these two lines right here, and this tells us about our net inflow and outflow. In almost all cases, it is net outflow, but not entirely. So this is showing our fractional rate of gas outflow versus distance to the host. You'll see a lot of scatter, but on average, we have higher net outflow as the satellite approaches. Now we can take this quantity and turn it into something like a depletion time by taking the reciprocal of it. I say like a depletion time because this is gas that's being expelled out of the satellite as opposed to gas being used up in star formation. But we're going to call this our gas loss time scale, so just 1 over the fractional rate of gas loss. And I'm plotting that on the y-axis of this plot here. And on the x-axis, I'm plotting time since quenching. So this dashed line, is time at quenching. Anything to the left of it is a satellite at a snapshot that has not yet experienced quenching. Anything to the right of it has already quenched. And we see that the red area is showing gas loss timescales, which are longer than the time until when the satellite actually quenches. In the blue region, these are gas loss timescales, which are less than the time until the satellite actually quenches. Again, there's a fair amount of scatter, which tells us that the evolution that these galaxies go through is stochastic. In other words, we can't entirely predict what's going to happen to the satellite in 3 gig-years from where it is at a particular point in time. However, there is a trend there, and it gets stronger as we approach the time of actual quenching, where we see the gas loss timescales are usually a few gig-years longer than the actual quenching timescale. That's because these satellites tend to quench before they are completely devoid of gas. All right, I guess I spoke fast, so let me throw up this plot here. This is about what happens, where does the satellite gas go? So to try and bring us back to the circumgalactic medium of the host galaxy, we can say, let's imagine I'm looking at this host galaxy, and I'm looking at either H1 on the left or O6 on the right. How much of that H1 or O6 comes from the main progenitor, and how much of it comes from an individual satellite? And you can see with H1, we're often looking at gas which is brought in by satellites. That gas tends to stick around closely to the satellite. When we look at O6, that's dominated by gas from the main halo. The main halo is providing metals, but it also is providing this hotter CGM. All right, let me put my conclusions up here. Yeah. And I'll take questions.
Do we have questions for Charlotte?
I have a question about the fact that you're basically saying there is still gas in galaxies that are technically quenched.
Mm-hmm.
What would the observational signature of that be like, particularly as we start to be able to look at dwarves beyond the local group itself?
Sure, so this gas is going to be low surface density, which is going to make the observational signature tough. But we would be looking for low surface density. H1 gas, maybe we could also see higher column densities in absorption around these.
Okay. Any more questions?
Thank you. Beautiful talk. I was actually to follow up on that question. What about the Milky Way, the population? Mary Putman, for example, has all these limits on the H1 for those galaxies. Does it match the number of the fraction of quenched galaxies for the Milky Way?
Yeah, in fact, if I go way back to the very start of this presentation, this code down here will take you to Aiken's 2021, and we do some comparisons to quenched fractions there. I also have a more recent paper which is focused on comparing satellite galaxies to isolated dwarf galaxies, which looks at H1 fractions. And yes, we are consistent with what the observations can tell us.
I see one more question, and
Awesome.
because Charlotte was, I see a question over there. Because Charlotte was a little short, I'm going to sneak in 1/3 question.
Hey, do you also explore what fraction of the satellite could be backsplashed and lost their gas due to tidal interaction and not the ram pressure?
Yeah, so these galaxies, this particular selection is only looking at satellites which are within the virial radius at redshift of 0. I've done some other work which includes backsplash galaxies. And what I can say is that we see gas loss happening at large radii, large distances from the host. So that's why we start our tracking at the first time it's within 2 times the virial radius. So that gas loss can continue at that point. The gas loss that we see at these large radii, which would be, if I go over to this plot, this would be gas loss that's happening in these sort of low values of script P. And we don't see as strong of a signature of ram pressure, but it still looks more like ram pressure than it does tidal stripping.
Thanks, Charlotte. And I am going to yet again call it and say thank you to Charlotte and thank you to everyone who gave a talk in this session. So we're having a discussion session now, which is also partially why I feel a little bit more comfortable cutting off questions. Also because we have a talk at 1:30 that has to happen exactly at 1:30. So the more questions and the more discussion we have, unfortunately, the shorter our lunch break gets, which is a great way to give Viraj the floor. So go ahead, Viraj.
Great. All right, so we have about 20 minutes until lunch. So we decided there were going to be 2 discussions sessions, but we decided to merge them into one so that we can have the theorists and observers talk to each other in the same room and share ideas. And so we put together a few questions to kind of guide the discussion, but this is really a time for you to raise questions you didn't get a chance to ask earlier, either yesterday afternoon or today morning. So one thing is we've heard a lot about CGM-based regulation of star formation in this particular session, but we also know that the local ISM conditions matter. So there's like the pressure-regulated, feedback-modulated framework that Chang-Gu Kim mentioned, and the superbubble feedback on small scales that Lori Porter talked about. So these are not mutually exclusive, but the question is, how do we disentangle these and constrain their relative importances? So thoughts on that. A related question is, how do we constrain ejective feedback, which is kind of blowing large amounts of mass out of galaxies, versus this more preventative form of feedback where you're heating the surrounding gas or even the ISM gas. We just heard from Charlotte, very nice talk about the role of the environment in regulating star formation and quenching satellites. So any thoughts on that? And then I'm very excited about all of the new observations that we're getting, like of the cool low ionization CGM and the CGM in emission. Is that going to be the things that help break degeneracies in our models? And then the last thing for the observers and the theorists is, what are the prospects for tracing the full baryon cycle with like real observations, maybe with metals or something? So, thoughts? I have some ideas, but I want to hear. Yes.
So I think one way we can distinguish between the two options in point one is timescales. So I think we would expect that for ISM type regulation, it's probably going to happen fairly promptly, as opposed to if you're regulating star formation or quenching star formation via a process that's associated with the CGM, that's probably going to happen on much longer timescales because that regulation is to do with truncating or shutting down or impeding the reaccretion of gas. And so I think one very clear signature we have that the ISM piece of this is operating is seeing how in the observations, when you have a merger, so you can see that there is a prompt event happening, that you see that soon after that merger happens, you have a high fraction of galaxies that rapidly quench. So that's not to say that that's the only way you can quench galaxies. I don't believe that's true. But I think that's one way that we can put a pin in one mechanism that can promptly and locally quench star formation.
Yeah, that's really insightful. And I think another tracer of these timescales probably comes from the metals. And so maybe the abundances of different elements in the ISM and in outflows can constrain this?
Is on? Yeah. I wanted to say that there's some things I cut from the review, but one of the things that the cosmological simulations are showing is that the so things fluctuate on long and short time scales, and it's the long, if you do a PCA analysis on sort of these excursions away from the average, that it's the long time scales that dominate. So I do get your point that I just think both will be important. So you still need the long timescale regulations, even if it's initially driven by short timescales.
Yeah, I want to make a related point to what both Sarah and Freke said. So in general, when we look at CGM, if it's not radiation driven, we are actually seeing winds that have started millions, actually hundreds of millions years back. So I think it's kind of very important to connect CGM properties that we see today to the star formation history rather than just the star formation happening at that point. And if we can actually have good star formation history, maybe we can actually distinguish between the feedback processes as it goes, around, at different distances in the CGM.
Yes, agreed. The star formation history is very important.
I was just going to ask a general question on the mass loading and the metal loading because it was discussed a lot during the session. Is there any sort of kinematic signature that you can get in observation that from these different feedback processes that are used in simulation that one can, as an observer, go and check in the, say, in the outflow velocity or something that would say that tell us anything about the feedback that's going on in the galaxy, instead of directly measuring the mass loading factor, I was wondering if there's some other observables that as an observer you can go and look out for that could distinguish between these different feedback processes.
So to answer that directly, one of the things you can do is take high-resolution spectra of absorption and emission line profiles, and the shapes of those profiles, once you account for effects like geometry, you can actually infer the shape of the velocity field of these cloudlets that are entrained in your outflow. And so that will actually inform the driving mechanism. And so if you see, say, particularly steep velocity profile, that will indicate a completely different physical mechanism from something that's more shallow. And so you really need to get good high-resolution spectroscopy. It might be really nice if you could do that in a spatially integrated way in the ultraviolet. If anyone can think of a way we could do that, that'd be great.
Hello. Yeah. So related to that point, so in the upcoming paper from Mark Foyt, where all of us are that you've seen here are also co-authors on, he makes an critical point that the specific energy of these outflows are very important, and that specific energy encodes not only just the thermal energy but the kinetic energy as well. And so comparing the specific energy of these winds and I showed this in the schematic graph later, that the specific energy of these winds compared to the specific energy of the halo is actually a very important threshold here. And so getting precise constraints on the specific energies of these outflows, and if you find them consistently larger than the specific energy that you may expect for baryons which are accreting onto the halo, then this is actually, you can sort of try to place yourself like on that schematic graph of where of whether the feedback is most effective, and whether it's you expect it to be in the uncoupled mode or the coupled mode. Because if the winds are uncoupled, then there's a sweet spot where you expect the winds to be maximally efficient. And so if your specific energy aligns in that region, that could tell you something about how the winds are regulating the star formation that's in those galaxies. And so getting a handle on that specific energy, both thermally and kinematically, can make that comparison between the energies, I think, a lot easier and be quite informative in an indirect way.
I think I would like to return to Sophia's point about spectral line profiles in both observations and simulations. One of the things that we don't always do a good job at is mock observations, and we don't put enough effort into, I think, as a community, into really trying to make sure that we can get really good comparisons to simulations. It's not enough to just come to a conference and show that your simulation showed this, but what's that going to look like in an observation? Having done this for a little while, I'm finding, the devil is in the details, and there are some challenges that we find, and some concerns that we have about the way that we sometimes interpret data. So looking at line profiles and simulating line profiles is really fantastic, because we can get away from ridiculous things like column densities.
Yeah, no, that's a really good point. None of our simulations are ever going to be perfect, and so there's also this question of how are you going to deal with that. And also, if you want to use the observations and these mock observables to infer something about what the parameters of the simulation should be, how are you going to do that?
So maybe just a quick comment going back to point number 1 on how we see either local ISM conditions regulated star formation versus more like large scale properties like the CGM. So I think in the first couple of days we talked about a lot about the fact that the star formation efficiency per free fall time is just a few %, which different models predict as a result of localized stellar feedback. On the other hand, population properties such as the star formation main sequence, when we look at the specific star formation rate of galaxies and how that evolves with redshift, which evolves with redshift in a way very similar as the inflow rate onto halos, I think this is, very interesting evidence of sort of large scale regulation as well, and connected to star formation histories.
And also, since you mentioned this and you're giving this talk tomorrow, we're focusing here, I think, a lot on lower mass systems and Milky Way mass systems, but you can get a lot more data in massive groups and clusters in terms of the CGM and the ICM. And so also thinking more about that end and how we can pin down our models using data on more massive systems. Great. Well, I think we still have 10 minutes, but we can go to lunch. I have one question. So something I've been thinking about with Chris and Greg at a high level. So I think Sarah or someone mentioned star formation histories are crucial constraints on how star formation is regulated, right? The timescale issue. For people here that work on chemical evolution in the observations, right? Do we have something analogous to like star formation histories, but in terms of like metal production or metal enrichment histories? We can do this for like nearby galaxies, you know, counting up resolved stars, I think. And I think the combination of star formation histories and chemical enrichment histories may be able to break some degeneracies in some of these models, but I want to hear from like the observers. Like, what are your thoughts on, you know, the status of tracking metals in different phases and different zones, not just right now where they are, but also over like the evolution of individual systems or populations of systems, if that makes any sense.
I don't have an answer about metals particularly, but I think something that is worth noting particularly about, you know, if the goal is to do this in some sort of holistic way, when it comes to observations, you know, we need to kind of look at the same systems. You know, the outflows are multi-phase, and different sort of very different and very intensive observations are needed to trace different ionization states, different energies that are going on in these systems. And so, you know, I think in some sense, something that would be really valuable is, I don't want to say consensus, but like, you know, somewhere where, you know, we can focus efforts using very different observational probes to actually get a pin on these different processes in the same systems, rather than just having one tracer in one system, different tracer in another system.
So on the point of looking at the chemical abundances and trying to tie that back to a sort of enrichment history of gas, I guess I want to plug Fari Zahadi's work, who's done a lot of very detailed analysis of the relative abundances for the cool phase of the circumgalactic medium, and found excess iron relative to alpha in the sort of inner CGM of quiescent galaxies, which suggests a sort of late time enrichment where the type 1As have gone off, at least for the lower star formation rate systems, whereas the star forming ones are more alpha element dominated, as you might expect.
All right. Any other last thoughts before lunch? All right, I'll leave you with one more, and that is, could any of these things vary with redshift, right? So like right? I mean, in terms of like, does it, right? Yeah, but constraining that, right? So like, is feedback ejective at high redshift, but becomes more preventative at low redshift as hot halos form? I don't know. So talk about that over lunch. And mass. And mass, and everything else. Yeah, yeah. Okay, thank you for a great discussion.
Thanks a lot, Viraj. Thanks, Katie. And wonderful discussion. Just two announcements. First is that there are still some beers left over from yesterday, so we will have something before like the dinner and like after the end of the day. And second, we have to be back exactly at 1:30 when Jason Tumlinson will give you an overview of the habitable worlds. So yeah, we are going away for 1 hour, 5 minutes exactly. Thank you.